Merci beaucoup, Philippe. You know, that's probably my French. And I apologize, 12 years in New York City and now, almost 8 years in Southampton, completely lost my ability, to... I pick it up. You pick it up, that's excellent. But it's really good. Thank you very much for the invitation, Pip. And, it's really good to see, old colleagues or colleagues, from the past. Really good and exciting. So before I start, talking about CO2 storage, and this is a slide from Iceland in a project I was involved. I have to say, my life is not that grey. I mean, it's much brighter and more interesting. But sometimes, the weather in Iceland can be really harsh. But what I will try to do is kind of give an introduction why we think about carbon capture and storage. And then I move on, to kind of a special way or a really permanent way to take care of CO2 emissions, and that's, through mineralization. And this is really, work that started during my postdoc, from 2001 onwards. And at that time, basically, there were two groups, I and somebody else at Pacific Northwest National Lab, thinking about, the mineralization of CO2, and you can see why we are thinking about that. But first, before we talk about storage of CO2, we have to kind of understand the global carbon cycle, or the anthropogenic perturbation of the global carbon cycle. And I know, these numbers are from 2017. They changed a little bit, but what you can see here in blue are the fluxes, And the fluxes are in gigaton of CO2 per year. These are global fluxes, so roughly, from fossil fuel industry, the emissions of CO2, here, 34, they are roughly now, 35 to 40 gigatons per year are emitted, by burning fossil fuels into the atmosphere. So we use the atmosphere as a disposal reservoir for our CO2. But, some CO2 is absorbed, by the biosphere, by the vegetation. So there is a land sink and there is an ocean sink, because some is absorbed by the surface ocean and is stored in the surface ocean, which produces, the ocean acidification. But as you can see, this is huge. That perturbation is really, really huge. And in simpler form, basically as a kind of a mass balance, you can see here that the sources, 88% are, from fossil fuel burning, our industrial activities. 12% are from, deforestation, land change. And then, the major sinks are, the atmosphere. 47% of that annually emitted CO2 stays in the atmosphere. It produces, that global warming. 30% are basically taken up by the biosphere, land sink, and 24% of that, emissions are absorbed by the surface ocean. There's a little, imbalance, which we basically don't really know where that is right now. But what that produces, and you obviously know that, is kind of the global warming, because we change, through the greenhouse gases, we change kind of the energy budget in the atmosphere. And you can see that we here, is kind of global warming relative to the 1850, 1900, as, a function of time. Here in 2017, we were here, we are here now, but we are on that trajectory. Okay? And that means you see here some scenarios that are modeled, and it really depends, in terms of the warming, where we are on that trajectory. But, human-induced warming since the Industrial Revolution is roughly 1 degree Celsius. So it doesn't sound like a lot, but it's quite a lot. And that has obviously for the global climate system a huge impact. So the task we have is basically we have to reduce the CO2 emissions. And as you know from the IPCC reports, we have to do that drastically or rapidly, because we don't have that much time. And here you can see billion tons of CO2 per year emitted. Up here, you know, that's the numbers from 2018, 40 billion tons of CO2 emitted. And really now, you know, the task is to 2050 that we are basically zero CO2 emissions. No? So that's a really big job, and it really depends where we are. And if we are on that pathway, we have a huge overshoot, you know, of the CO2 emissions. That means, you know, from 2030 to 2050, we have to take CO2 out of the atmosphere or reduce, you know, the input in the atmosphere much quicker than if we start early that job. So there's one practical problem in that. And we experience that right now, you know, with the war in Ukraine and the dependence on fossil fuel from Russia is, you know, our prosperity of the developed world is built on fossil fuels. Everything. And, you know, the full replacement of fossil fuels is not possible, you know, from today to tomorrow. It takes decades. And that has to do, you know, with the life cycle of our infrastructure. So we have roughly, you know, 10 to 20 years to clean up. That's the job. But the dependence on fossil fuel, you can see here, you know, that's from, you know, the BP, the Statistical Review of World Energy. You can see here in different colors the world consumption in exajoules, in green oil, natural gas, coal, and then nuclear energy, hydroelectricity, and renewables. And you can see the big part of our energy here in 2020 is still, you know, coming from fossil fuels. There is a dip, that's, you know, the COVID pandemic here, but it's already increasing again. So, you know, that's our dependence. And that dependence, you know, is huge. And we can't, you know, speed up the renewables as fast as we should in terms of, you know, the global warming we produce. So we have to find a way, you know, how we can clean up kind of the fossil fuels. So we have to find mitigation pathways. And mitigation options, you know, there are two options. You can reduce emissions and you can increase carbon sinks, natural carbon sinks. And if we, you know, reduce emissions, you can increase efficiency. You can change the fuel mix, you know, from coal to natural gas, for example, and then you can substitute renewable energy sources for fossil fuels. That's obvious. You can increase the nuclear, you know, use of nuclear energy. You can do carbon capture and storage, so that's the topic of today. And you can do carbon dioxide removal. That's basically taking CO2 directly out of the atmosphere. The other options, which I will not talk about, are kind of increasing, you know, the sinks, where, you know, CO2 is stored for several hundred to thousands of years. So if we move, you know, to carbon dioxide capture and storage, basically, you know, the whole thing comes, you know, from the oil and gas industry, because the oil and gas industry knows how to, you know, pump fluids in and out of reservoirs. And they have, you know, the knowledge, detailed knowledge of the subsurface. So initially, you know, basically what carbon capture and storage is, you capture CO2, you know, mainly from stationary sources or directly from the atmosphere, which is not here. You capture that CO2, you transport it, and you can inject it into the geosphere again. You can injecting it into depleted oil and gas reservoirs, into depleted gas fields, or in saline aquifers. That's kind of, you know, the general view for carbon storage. So what carbon storage or capture and storage is, it combines, you know, you capture CO2, you transport it to a storage site, and then you have to do the monitoring and accounting to basically prove that your CO2 is permanently stored. There's one problem. If you look at, you know, injecting CO2 as a single phase into a deep geologic reservoir, that's the density difference. You know, your CO2 at a certain depth, generally 800 meters and below, is a supercritical fluid. And that supercritical CO2 is less dense than your saline groundwater in the pore space. And that density difference produces, buoyancy forces. So it's the CO2 is buoyant and rises up in your reservoir. And if there is no cap rock, on top of your reservoir, that CO2 over time will come back because of that, of that effect. Obviously, with time, CO2 will dissolve into your brine, and then it will react with the rocks, and eventually in certain type of rocks it will mineralize. But that's, that buoyancy is very critical in terms of safety and, the risk of CO2 storage in geologic reservoirs. So, as you also know, as hydrogeologists, the geologic subsurface is not a leak-proof container. There are fractures. There are, abandoned boreholes. So there are pathways, from a storage reservoir where CO2 could move up through that buoyancy effect and then leak into a shallow drinking water aquifer, contaminate that aquifer, or even, leak back into the atmosphere. And that's, what we want to avoid. And that's what we have to do monitoring for. But then, in 2001, 2002, we had the idea that, and the idea is based on nature. How is nature taking care of CO2? Through weathering. So weathering, basically, of rock neutralizes CO2. And that's, certain type of rocks, like calcium, magnesium, silicate rocks, like this peridotite here, or basaltic rocks, react with CO2 and convert CO2 to calcium, magnesium, iron carbonates. We know that from nature. We can observe it in nature. Here, for example, in Oman, you have these travertine terraces. They're exactly CO2 that was absorbed by high pH, pH 11 fluids, reacts, with the calcium in that water, precipitates calcium carbonate. Here, you can look in the fractures and cracks in the same rocks. They're full of magnesium carbonate. That's what over time, happened. Here you can see the same, core I drilled in Iceland. You can see the fractures have calcium carbonate in it. So that is our goal. That was the main goal was we want to mineralize CO2. In order to mineralize that, as I mentioned before, you need magnesium or calcium silicate-rich minerals. Has to be silicate minerals, and these minerals like olivine, pyroxene react with water and CO2. Here, to another mineral called serpentine, which is hydrated olivine, and to calcite or magnesium carbonate and calcite here again if you have plagioclase. And we studied that in the laboratory. What is the rate of these minerals? The dissolution rate. So basically, in order to react with the CO2, you have to dissolve these minerals to mobilize magnesium, to mobilize calcium ions. And, there are a lot of studies, that study dissolution rates, like here it's the log rate of magnesium release in moles per square centimeters per second of certain silicate minerals and also basaltic glass. And you can see that obviously at acidic pH, these minerals dissolve faster than at more neutral pH, and some silicate minerals have an increased dissolution rate again at higher pH. But generally, acidic conditions obviously attack the rocks, and magnesium and calcium is released, and all these these minerals are basically occurring in mantle peridotites. Usually, these rocks are deep in the mantle, or in basaltic rocks, which are volcanic rocks. If you go to sedimentary reservoirs, like here the Utsira sandstone in the North Sea, where Statoil is injecting CO2 in it, you can see that the fraction, the percentage of injected CO2 mineralized is basically nothing, even after 10,000 years. Why? Because this Utsira sandstone has no reactive minerals, has no plagioclase, has no olivine, has no serpentine. And in other reservoirs, that fraction is much, much faster. But for us, the question is that time scale. How fast can we mineralize the CO2 in a reservoir? In order to answer that question, we went to Iceland. This was just, a side story. We were approached by the president of Iceland at that time when I was at Columbia University, and he said, oh, we should do a project in Iceland. There's lots of basalt. We have geothermal industry, so we have a CO2 source, as you will see in a minute. And, we got the support from the government in Iceland. So basically, we had a project here, close to Reykjavik. Reykjavik is here, just outside of Reykjavik. And we wanted to test, we knew from the laboratory, the dissolution rates, the reaction rates, but we didn't know it in a real world reservoir. So we set up a really small test. 175 tons of CO2, we injected and then followed up by 70 tons of CO2 and H2S, hydrogen sulfide injected. The hydrogen sulfide was the key interest of our industrial partner, Reykjavik Energy, because, geothermal power plants in Iceland can emit a lot of H2S. If you've been in Iceland, you probably smelled, the rotten eggs. And that's basically the H2S, everything smells shower, smells of rotten egg, and you think, whoa, what's wrong? But so we founded, a project, the CarbFix project. It was a collaboration between us at Columbia University, University of Iceland, Reykjavik Energy, and the people in Toulouse and the Icelandic Geosurvey. And what we did, this is basically, if you can see it, this is the geothermal power plant in Helles Heidi, 320 megawatt power plant, geothermal. It's wet geothermal. And with the geothermal steam, they produce CO2 and H2S, up to 40,000 tons of CO2 per year, and roughly, I think, 27,000 tons of H2S. As I said, the company was interested in H2S, taking that out, instead of emitting it into atmosphere, because there is legislation in Iceland that they have to mitigate, the effect of H2S. So we had a CO2 source, so we built a CO2 H2S capture plant here. We built a pipeline and we injected our CO2 back here into a basaltic aquifer. Here you can see why there is CO2 and H2S in Iceland. This is kind of a cross-section through, basically the mid-Atlantic ridge that, halves the island of Iceland. It's in the middle, so on this side you're on the American plate, here you're on the European plate, and there are a lot of geothermal systems here in Iceland, but the CO2 and H2S comes from a solidifying magma. It's natural. It is from, emitted, through this magmatic activity and comes out in the steam that is produced. Here you can see a cross-section of the injection process and the storage reservoir. So we were given a storage reservoir by the company, which was not ideal, in the sense that, our injection borehole was basically, it's a deep borehole up to 2 kilometers, but our target injection reservoir was between 400 and 800 meters. At 400 to 800 meters, the CO2 is still gases. In gaseous form, it's not supercritical fluid. So that means we couldn't inject pure CO2. Okay, that was the first one. So our injection reservoir was here. Between, this depth, we had an injection borehole and we had several monitoring boreholes. Okay, indicated here. The CO2 came by a pipeline, and we then also had a pipeline of groundwater which was pumped upstream, and we mixed the two. So what we injected in Iceland was, sparkling water. But the sparkling water had, a pH of 3. It was very acidic. It was CO2 saturated. And for that, we developed and built, now a protected kind of injection system that mixes the CO2 and dissolves, produces an enhanced dissolution of CO2 into water within the borehole. So that the injection system is installed in the borehole, and you can see that in a schematic here. Basically, what the idea in that project was, we CO2, we sparge CO2 in our water, then the CO2 dissolved in the water is injected into the basaltic reservoir as a single-phase fluid, as a carbonic, carbonated water that reacts with the basalt, and then, away from the injector, carbonate minerals precipitate. And if you're a geophysicist, you realize, okay, if we have a single fluid, we cannot really use geophysical methods, like seismic, to monitor our injection fluid. It's not possible because you don't have this, the difference is between the ambient groundwater in the reservoir and in your injected fluid. So we needed to come up with, geochemical methods to monitor what is happening with our injected CO2, and that's illustrated here what we used. So as I mentioned, we injected water, 2 kilograms per second of water was injected, and 0.07 kilograms of CO2 was injected, okay, here in the injection borehole. So in the water, we added a dye tracer, rhodamine G, and then we also added something like radiocarbon, and I will explain that, why we did that. And in the gas stream, we used SF6, sulfur hexafluoride as tracer, and SF5CF3. So we had all these chemical traces, conservative, non-reactive traces, were injected together with the injection fluid. Okay. And you might ask yourself, well, why did we use, radiocarbon, which is a reactive tracer, and it's radioactive, no? So we injected radioactivity in the subsurface. And, why did we do that? Because think about what's the most or the best tracer to trace carbon. It's carbon itself. And all the carbon in the reservoir is basically more or less C14 dead. It's old enough. So we could just spike our, CO2. We can change that, we can isotopically label it, from C12 to C14, and add a concentration that is in the injection well 5 times more than. So 5 times above the concentration of radiocarbon in the air we breathe in. And obviously there's huge dilution in the reservoir. So in the reservoir itself then, basically, you are below more than we can measure that now. And so every radiocarbon molecule, basically every radiocarbon we find then in groundwater we pumped out of the storage reservoir is basically our injected CO2. It's direct labeling. And with that, as you will see, we can do mass balance calculations. All the other traces are non-reactive. They don't change. They change only through, dilution, through mixing, but not through reaction with rocks. So that's the idea behind, using radiocarbon. And the test, and you're probably familiar with, something like that, the experimental setup was a forced gradient test. We had an injection borehole, where the fluid is injected, and we had a monitoring borehole, and that was pumped constantly. And it was pumped because the hydraulic gradient in that reservoir was too shallow, and we could wait, for decades for our injected fluid to arrive at that monitoring borehole without pumping. That was, the downside of the reservoir we got. But we overcame that problem by constantly pumping this monitoring borehole. So injection here, pumping here, forced gradient test. We moved our injected fluid to this borehole. So here now you can see results. So what are these? Are tracer breakthrough curves. And you can see here the concentration of SF6 in CC SDP, versus as a function of time. Our first injection was here, the 173 ton. The second one was here. And what you can see, if you look at the blue, which is the SF6 injection, so just let's focus on the blue curve now. And this is basically after 60 days, we had the first breakthrough in the monitoring borehole. So we collected samples constantly in the monitoring borehole. And then measured the SF6 concentration. And then, we had an increase, the highest peak, highest concentration of SF6 after 400 days. So remember, the shape of this, curve here. Maximum, that means, our injected solution, the bulk of it reached the monitoring borehole after 400 days. Here you can then see in this, we also monitor pH of the fluid in the reservoir, and also in red, the dissolved inorganic carbon in millimoles. pH dropped, Our injected fluid had a pH of roughly 3, so it dropped below 7. That, that indicates that our injected solution arrived here at that first peak, where we also had a peak of dissolved inorganic carbon. But then look at the dissolved inorganic carbon, peaked again a little bit here after the second injection, but then it's constant. Do you see a peak at 400 days after injection started? No. But our conservative trace showed that, huge peak. So the conservative trace arrived at the monitoring borehole, but not really our dissolved inorganic carbon. It was not there. You can look at the radiocarbon, exactly the same, shape. We didn't really get, that radiocarbon back in the monitoring borehole fluids. So you can also look at, the magnesium and the calcium, and let's focus on magnesium measured. You see kind of the same. Magnesium concentration in the fluid increased, decreased, and then increased again, but then, it decreased. And in the calcium, it exactly, kind of the same shape. So we mobilized calcium, magnesium, we dissolved it into the fluids, but then, it basically decreased here, which indicates if calcium and it decreases, you have precipitation of a calcium phase in the reservoir. So using the conservative traces, you can basically calculate the mixing between your injected fluid and the reservoir fluids. And for each water sample we collected, we can basically calculate that mixing fraction. How much of injected fluid do we have in that sample? Then you can calculate, using that data, you can calculate what would be the expected dissolved CO2 concentration in our collected water sample using, these mass balances. And the difference, obviously, from our sample to, what we would expect if we just have pure mixing in the reservoir is, giving you the difference. And that can be positive or negative. But this is illustrated basically here, in dissolved inorganic carbon. We have, kind of what we would expect if in the reservoir we only have mixing. Nothing else is happening. And we would expect this concentration of dissolved carbon in the reservoir. But what we actually measured was much, much less. This huge difference. So we lost carbon along that flow path from the injection borehole to the monitoring borehole. And so what does that mean? Our interpretation was that calcium carbonate precipitated, or a magnesium carbonate precipitated. The carbonate phase precipitated, so it was permanent storage. And, that made huge headlines because, basically over 98% of our injected CO2 was carbonated, mineralized within less than 2 years. Really fast reaction rates. And that means permanent storage of CO2. Because carbonates can't leak out of the subsurface. No? That's why, it's so permanent. It's the most permanent storage method. But this basically, was interpreted that, yes, our CO2 mineralized, and it mineralized really fast. Do we believe that? It's an indirect proof. So what we did, we drilled a borehole between the injection borehole and the monitoring borehole, and we recovered core, and within the core, we analyzed, we looked at any carbonate we could find, and if that carbonate has our radiocarbon signature. Okay? But as you also know, a borehole is just a needle in the ground, you know, and you have a huge reservoir, so you really have to be lucky, you know, to just find your precipitated CO2, because, you know, 170 tons of CO2 is nothing. It's really nothing in terms of the volumes. But what we are then interested in was basically, you know, we are in basaltic rocks or in periditic rocks, so the porosity is very important, or the relationship between total porosity and effective porosity is very important. And so we started to characterize, you know, the recovered core based on physical parameters. But we used clinical, you know, computed tomography, micro-CT scanning, and we also used something like micropositron emission tomography, PET. And we did core flooding experiments while we scanned, you know, the cores in the micro-CT or in the clinical CT. And what we were really interested in was to characterize or measure the total and effective porosity and the total and effective surface area, because surface area in terms of reactivity is very important. And then basically predict fluid transport and reactivity of the heterogeneous basalt reservoir. Here, you know, you can see just the CT scan section. Maybe it works, maybe not. But, you know, basically what you can do with CT images, you can then, you know, subtract kind of the matrix. You get the total porosity, which is here in red. You can then, you know, subtract basically, or just by image analysis, find where there is the effective porosity, mean where is the pore space connected to each other, and that's the blue one. So with this procedure, you know, you can really kind of come up, you know, with the total porosity of that core section, and you can calculate, you know, using, you know, image analysis software, the surface area of the pore space. And obviously you can then also, from the total porosity, if you do this image analysis, you can get the effective porosity. Which is here, no? Which is obviously much smaller, you know, the connected porosity in vesicular basalt, you know, where you have vesicles, is obviously much smaller than the total porosity, but that's, you know, what we did. And why is that important? You know, it's important in terms of injectivity. You know, how much CO2 can I inject, or fluid can I inject over time? And then, you know, with the micropositron emission tomography, or micro-PET, we basically looked at the connected porosity and the effective surface area. So what is micro-PET? It's basically also a scanning, computed tomography scanning, but you add a very short-lived, you know, radioactive tracer. And you inject that radioactive tracer in a fluid-saturated core, and you scan for it, and you can see the flow paths through that core. You know, you can image basically at real time how fluid flows through, you know, this connected pore space, and there are obviously differences. Here you have just one fracture, more or less, and here, you know, you have a more connected porosity, and the color coding basically shows you the concentration of that radio tracer. And with that, you know, we can then kind of characterize the pore, you know, size distribution, and do some calculations. And, you know, that was in work together with Chris Zachowski at Stanford University. So what he did is a stochastic vesicle percolation simulation, basically looking at the distribution of these vesicles, as, you know, and then get the relationship of effective porosity versus total porosity. And what we have found out, you can see that here on this backscattered images, it's not just the vesicle, you know, the hole in the basalt core that's important, but it's that cracking network that goes, you know, away, basically radially goes away from these vesicles, that adds microporosity to, you know, in the basalt, and that microporosity is very important for, you know, the connected porosity, and also for the reactive surface area. So if we have no microporosity, you know, then you can see that the effective porosity is really lower if you have, 20%, porosity, you have very low effective porosity. It's not really connected. But if you have these microcracks, you get the connection between the vesicles. And so what he then found out, experimentally and through these simulation results, and all these points are other data, from other authors, and this is basically his data. He found out that you really, in order to have a decent injectivity in basaltic rocks, you need, a kind of a total porosity of at least 20% to have an effective porosity that is basically higher than 10%. So this is, this is important in terms of, maintaining an injectivity in these rocks. So to move back, just a minute to the carbonate minerals. Yes, we found carbonate minerals, in our core. This is illustrated here. You see concentric growth of new carbonate minerals in a vesicle. And, we also found a lot of carbonates in our infrastructure in the monitoring borehole. Basically, that submersible pump was just carbonated, and stopped working. And if we looked at the carbonates we found in the reservoir, we basically found our radiocarbon again. It had our signature of the radiocarbon. So with this, we had also the proof, yes, our CO2 was mineralized. So, is that really relevant, 173 tons of CO2? No, it is not. But now, Carbfix is a company. So based on our work, Reykjavik Energy founded a company. You can visit them of www.carbfix.com, and they upscaled from 2014 to today. So they inject CO2 at the edge of the geothermal reservoir. And they injected, soon up to 40,000 tons of CO2 and 16,000 tons of H2S, and they claim, that it's carbonated, and the sulfur basically is also, mineralized to pyrite, which is iron sulfate. So that's, what they commercially are doing it. They're doing it, for carbon credits. So, for example, Bill Gates, buys their credits and reduces his carbon footprint this way. For that, they developed basically a modified carbon capture process from the geothermal steam. It's very simple, It is basically a column, and it's a washing tower, and the CO2 and H2S have a high solubility. So they get dissolved in that water stream, and what's the non-water soluble gases are basically vented, that's nitrogen, and 1% to 2% hydrogen. But, with this, they basically have, a very simple way to capture CO2 as soluble gas in water. And does it work? The mineralization here, you can see some data, similar mass balance calculations, the expected concentration versus the expected one based on mixing versus, what they measure in the reservoir. I don't go in detail into this, you can read that in this paper, but basically Carbfix claims their CO2 is mineralized in an effective way, within, 5 years, what they inject. And with that, they basically came up, with a CO2 capture and storage process that is $25 per ton of CO2, which is extreme, which is there. It's quite cheap. The biggest, cost in conventional CO2 capture is between, 80 to 150 ton of CO2, just the capture process from a fossil fuel plant. So they developed really something that's economically competitive. So here, the key message basically, what we proved, and based on that research work, Carbfix developed a commercial process. 95 to 98% of our injected CO2 has been mineralized within less than 2 years. That is really what made the headlines. And, the target basalt storage reservoir should have a minimum total porosity of 15%, but it should be higher, in order to maintain the injectivity. And then, you know, they basically proved that it's economically feasible to store CO2 in basaltic rocks. Is basalt relevant, you know, worldwide? Is it, you know, a reservoir that's available? Here in red, you can see the global distribution of continental basalt. So you find on every continent, you know, you basically find basaltic reservoirs. Are they feasible or are they suitable, you know, for CO2 storage? Obviously not all. Some colleagues calculated, you know, theoretical storage capacity, which is in the thousands of billion tons. And I would also like to point out that the ocean crust, so offshore, you know, the ocean crust is all basalt. So basalt is the most common rock type on Earth. So it's not that difficult, you know, to find a reservoir for CO2 storage. But let's keep that in mind now. It's a huge challenge. And obviously, you know, what I showed you is not the only solution. And we need multiple solutions, and that's illustrated here. If you take 6 gigaton of CO2 per year, which is 20% of the total CO2 fossil fuel emissions in 2010, sorry, that's old data, but it's 20% of the fossil fuel emissions. And if you calculate what's that, you know, in terms of, you know, the volume at reservoir conditions, you know, assuming CO2 density of 600 kilograms per cubic meter, you can see kind of what the scale will be. You know, the global oil production is 1.5 times to the 7 cubic meter of oil per day. That's 80 million barrels of oil and 240 million barrels of treated and re-injected water, you know, produced by the oil and gas industry. If you compare that, you know, to basically, you know, the CO2, just this 6 gigaton of CO2 per year, this 20%, you can see that the size of the carbon capture and storage for 20% of the total fossil fuel is the size of the current oil industry. That's what we need. And so that's a huge challenge. You know, we built that infrastructure, oil infrastructure, over 100 years. Now we don't have 100 years to build that CCS infrastructure. So you can see that CCS, yes, can make a contribution, but it cannot take care of all the global CO2 emissions. That's important. And just an outlook, what's going on, you know, in my research group. So what we did in Iceland, we just right now apply, you know, to mantle peridotite, illustrated here. You know, this is kind of an overview drone image of Oman. And Oman, you know, is famous for the ophiolites. And ophiolites, you know, one part of the ophiolites are mantle peridotites, and mantle peridotites are rich in magnesium silicate minerals. And there, you know, we just did recently, you know, a small test. We injected you know, very small amount, 229 kilograms of CO2, you know, using kind of this infrastructure. We injected CO2 here, and in that monitoring borehole, you know, we then measured exactly, you know, what we did in Iceland, and we now, you know, analyze the data, how fast that mineralization was. Why is Oman interesting? Oman has one of the largest, you know, ophiolites. It's in an oil and gas region. It's the Gulf, you know, Persian Gulf and Gulf of Oman. So there's huge potential for CO2 mineralization in this country and in the United Emirates. And that's, you know, what I currently develop with this company, you know, 4401, in a similar way, you know, what we did with Carbfix in Oman. So I'm overrun, you know, heavily, but thank you very much.
You inject the CO2 in liquid form, it dissolves in water, and then the mineralization happens in situ.
The mineralization happens in situ, yes. Basically what we do, you know, we have a pipe in the borehole that brings down the CO2.
Okay.
And we have a pipe that brings down water. And at a certain depth, we mix them. And, you know, CO2 dissolution increases with increasing pressure.
Okay.
So you could do that mixing on the surface using compressors. But you can use the hydrostatic pressure working, you can use that. It works for you, and you can dissolve more CO2 at greater depth. No?
Okay.
Yeah.
Is there a risk of fractures or seismic problems when you inject water?
Yes, very good point. Oh, yes. And, we measure basically microseismic tremors, I would say. It's not really earthquakes, it's tremors. It's magnitude, -1 to maybe, a 1. Yes, but in this type of rocks, in more tight rocks, more low permeability rocks like peridotite, imagine that, if you carbonate olivine, which is a dense mineral, to a lower density mineral, which is a magnesium carbonate, you have a volume increase in the subsurface. How is that volume increase accommodated in the subsurface? It produces a stress in the subsurface, and we have studies that show that you crack the rocks. So imagine that cracking could help you, to produce more surface area, more permeability. So we call that reactive cracking, reaction-driven cracking. No? So you have a cracking front in the reservoir. And that works when the reaction is really fast. Pressure, you crack. You mineralize, crack, mineralize, crack, mineralize. That's the idea. And has been tested, in laboratory scale. It occurs, but, not in field scale.
And what is the impact of having high levels of carbonates, magnesium carbonates in the crust?
What is
the effect of having higher levels of magnesium carbonates?
In the crust, it's a mineral, no? It occurs naturally. So, but there could be an impact on groundwater. When you dissolve basalt and peridotite, you also mobilize, heavy metals, or you can. Like in Iceland, we tested that. So we mobilized chromium, we mobilized, or in peridotite, nickel, etc. But these minerals also, or these metals, over time also precipitated in carbonate minerals. So, they are not really mobilized. They don't stay dissolved in the water over time. But it's very critical that you monitor, for heavy metals, because that could be, a pollution risk of water resources.
Yeah, it's something related. What's the strategy of injection? Because I imagine that when you inject, then you clog rapidly the porosity and the permeability around the well. So there is a strategy or a design for injecting. So you are stuck of injection, and then what is the creep that you have to do in terms of water to be efficient?
Yes, so far, the longest injection that occurred, is in Iceland. So over, since 2014 to now, basically permeability and injectivity does not decline. It's not decreasing. Why? Because, you don't get precipitation close to the injection well, because the pH there is, 3. It's very acidic. You get precipitation of carbonates in the far field of your reservoir because the fluid, has to reach a pH of, neutral pH to more alkaline to precipitate carbonate minerals. But you are right that we do not really know the longevity of these reservoirs because of that clogging effect. And, that over time will occur. This is not just, there is, a certain amount of pore space available where you can clog, and then your injectivity will decrease. So there is a limitation, but these reservoirs are big, and to my surprise, in that geothermal reservoir in Iceland, this is kind of 1,000 meters depth, and for me, fractured system, really high permeability, which was very surprising. For these systems, but it seems like, especially in Iceland, that you have high permeability geothermal systems, and there is, the porosity available for this mineralization. But generally, mineralization occurs in the far field. That's, the mole, and not close to the injection borehole. But you're right, you could do stacked injections. Agree with you. You can have horizontal wells. So the Iceland wells now, they are all inclined boreholes. So there are different ways to engineer your reservoir for, efficient mineralization.
For magnesium silicates, is it common to have more than 15% porosity, or is this just special for Iceland?
Special for or some other places. That's the tricky part. No, I mean you can. Columbia River basalt in the United States. You have these interflow zones in continental basalts where you have kind of like a rubble zone, and then you have very dense basalt, and then again a rubble zone, and there it's like a layer cake. You have very high porosity, but peridotite, like mantle peridotite, low probability, especially if you go deeper. So now in Oman right now we think about fracking. Or you, yes, but it's interesting. I don't really call it fracking because in these periodites you have a high density serpentine network pre-existing. A crack network that's mineralized with serpentine. Serpentine is a ductile mineral, weak, and so you can imagine you don't need that much pressure to open that again. So that's the idea, but yes, basalt, certain places, really high porosity and injectivity. Peridotite, quite questionable, and the challenge.
Thanks for a good talk. That was really interesting. I love that. Wondering what you were doing.
Yeah, thank you.
A question a little bit in the same direction. With this, I didn't quite understood this porosity, 20% porosity questions. And I would have assumed that most of the flow at the reservoir scale is driven by fractures, and so the sort of matrix porosity is not so relevant, but maybe this is the case where...
No, I mean, it looked like, in the case in Iceland, we only have, that Iceland data. In that basalt, kind of the matrix flow, was the important one. That first peak you could see in the tracer, that was a fracture. That was a fracture basically connecting, our injection borehole with a very discrete one, no? But most of our injected fluid was not flowing in this fracture, but was more in that interconnected, micro porosity pore space in the matrix. Yes, but you're right. Again, going to peridotite, it will be fracture dominated. Yes, and then that question, of total porosity, that's less important. Yeah.
I have a completely different question. I was just thinking about the diagram where you showed the reaction times, and suddenly I was thinking of you remember the big buzz of the Dolomites, how they developed in the 19 and suddenly I was thinking, are there any experiments where you also work with microbiology as a catalyst? Because
yes.
In the Dolomites we know that these huge masses
yes.
of
Yes, good point. In several experiences. In Iceland, we have bad experience with microbes. So, the second injection, which I basically didn't talk about, the 73 tons of mixed injection, CO₂ and H2S. When we did that injection, after days of injecting that, injectivity went to 0. Injection borehole clogged. And then, we discussed that among the scientists, and I said, okay, yeah, that's oxyhydroxide minerals, that's common. We mobilize a lot of iron, just, do what oil industry does, inject a cocktail of different acids and, kind of nasty stuff, which didn't work. And then, French came in and they did an airlift test in the injection borehole. What came up was biofilm, all biofilm. And what happened was basically in injection borehole, we have CO₂, a carbon source. We have H2S, an energy source. And that cocktail, with a little bit of oxygen, in the injection borehole, produced a bloom of biofilm clogged our injection borehole. That's why, Carbfix then moved to the geothermal borehole, because at 220 degrees Celsius there is no life. There are no microbes. That's why, for them it didn't really work in that shallow reservoir because of this microbial interaction. But in terms of, in peridotite, we are now working with microbiologists and biogeochemists together. If, certain microbes in situ in this reservoir could help, precipitation of carbonates, which we know exist. And, if you go to peridotite, you see 3 different types of carbonates. In the shallow subsurface, down to 100 meters, you see calcium carbonate. Below, you see dolomite. And then, even further below, you see magnesite. So you see all 3, but microbes, could work for us. Depending on, you change, obviously, you acidify, you completely change the in situ environment, no? But yes, that's a work in progress.
There's a question from the beginning.
Thanks for the talk. There is, I don't remember exactly how many projects on the Earth it's related to CCS. I think it's around 20. But most of them are from EOR and then soil recovery. And the people defend that. They said better place with the CCS is offshore. We have plenty of basins, sediment basin everywhere. We can do it there. And now we propose on the basalt prospection. But if we know now that the most polluted people on Earth is the US, China, India, that means these guys are going to have to drive their fluids to your place, where actually it's possible to store the CCS, the CO2, sorry. And yes, admit that, okay, everybody agree that we have to store there, but in a few years, probably politicians will change and say now everybody has to take care of their own CO2. The producer have to take care of the CO2. And how we can explain to, let's say, Switzerland, okay, you have CO2, and people say, okay, no worries, we just send to Norway, there is no big deal, they're going to take care of that. It's like the same history that nuclear waste 20 or 30 years ago. And what would be your explanation for people, no scientists, for people which you have to convince them that CCS is the way to go?
Agree with you. In Oman, when we started, we had a huge project, Oman Drilling, which was not about CO2 sequestration, but we looked at the natural carbonation that is happening in these rocks. Omani authorities, even the public, turned against us. Said, you Americans and, Brits and European, you come in and you think you can export all the CO2 emissions to us, and, it's all we will be the dump ground, the dumping ground of the world. And we said, no, we will not do that. And we left it, to the Omanis, and what 4401 now does is they don't, they will not import, CO2 from out. They say, okay, it is for the in-country produced, in the country produced CO2. So Switzerland is an interesting case, no? So what Iceland now is selling, and what Norway is selling is, we take care of all the European CO2. Just send it to us. Iceland right now has a European project that is, building a terminal and basically ships. And recently in the newspaper was a ridiculous, and I have to be honest, ridiculous article about, an incineration plant in Switzerland, which is part of that Icelandic project, is shipping their CO2 to Iceland. No? Now you can think about what is the footprint, of that. So I agree with you. No, you need multiple solutions. So maybe in Switzerland you do not have reservoirs, for CO2 injection. There are studies out. So there's other, obviously other solutions you have to do. No? It's not everywhere you can do CO2 storage. I agree. It's not everywhere safe. But I'm and it's not only, mineralization. Yes, mineralization is the most permanent way, but it doesn't work everywhere. And I'm pretty sure that you can find sedimentary reservoirs, like, for example, what the Norwegians use in the North Sea. Since 1991, they inject 1 million ton of CO2 into a deep saline aquifers below the North Sea. They monitor that, so far no leakage occurred. It depends. If you have a large, kind of open reservoirs, you can do that. You can do that safely. It comes to monitoring and accounting, to just basically provide that proof that it's permanent. But we need a lot, we need a lot of different solutions, and that's just one. That can contribute maybe 5%, 10% to the solution, or even less. So it is certainly kind of country specific. I agree with you, because export of CO2, is a tricky one also in terms of regulations. And can you claim that then as a country for reduction? That's really open questions.
Yeah, because now some politicians are bigger and boss, let's say.
Yeah.
It's okay, we do like this, but probably in 10 or 15 years, they're going to be other bosses.
No, I agree. It's a big issue. Yes.
Because this is what happens right now in Europe. They say, okay, we just send it to Norway. And that's
Yeah.
it.
Yeah. Yeah.
C'était une dernière question où on clôt. I think we could spend the whole night.
Yeah. No, thank you. Thank you very much.
Merci à tous.